Try speaking. Yeah.
Sure, it seems it works.
Okay.
Yep, awesome. Can I get it started? Yeah. Okay, so, yep. Can you test, Lizy?
Yeah, I think.
Okay. Yeah, it seems it works.
Am I audible yet? Okay.
Yeah, very good. Yeah, so let's resume ISMM. This is Jung Ho An, who is chairing the third and fourth session. And it's my great honor to introduce Professor Lizy John. She's a Throughput Foundation Chair in Engineering at UT Austin. Her research interests include workload characterization, performance evaluation, and high-performance architectures for emerging workloads. I want to emphasize that she also conducts research on main memory controllers and allocators. She received many awards, and I don't have time to enumerate all of them. And she is an IEEE, ACM, AAAS, and National Academy of Inventors Fellow. The title and abstract, I just took a look. Reduce, reuse, recycle looks very intriguing to me. Let's welcome Lizy.
Thank you, Jung Ho. And it's my first time at ISMM. And someone this morning remarked, "Are you at the wrong conference?" Okay, I hope I can speak some things and bring architecture and some of the memory allocation issues together. So at the end, I never felt I was at the wrong conference, but at least one person asked me. Anyway, professors go and talk, but students do the hard work. And I would like to say thanks to my students, and especially Rui Havo, who did memory allocation work. He defended his PhD on allocation and memory management, and he's at Meta now. So probably some of the hard questions, if very specific, may go to him. But I also want to say thanks to the University of Texas that gave me the chance to have colleagues such as Professor John Goodenough. He worked on lithium rechargeable batteries. He received his Nobel Prize in 2019. And also Bob Metcalf, who was my colleague for about 10 years, and he won the 2023 Turing. But let's get to the topic. Memory is a scarce commodity. Probably you heard recently all these sorts of things. The memory companies, the stocks have this is just the last 6 months, how much Micron technology price has increased 5 or 6 times. SanDisk and companies who are making anything using DRAM, they all have quadrupled or more, 5, 6 times in just 6 months. And there are also all these blogs that you could read about. Even if we had all the money, there is no way to make the memory, like fabrication. Simply fabrication of enough memory is not possible by the world. There are no fabs to make the memory that AI needs. But this is the community who realized long ago that we need to manage memory well. Not now because the stocks are going like that or Wall Street bloggers are blogging. That's not why we were working on memory. This community was working on memory for lots of years and tried to use it well. That has been our goal for lots of years. Now, just coming to the big world beyond maybe computing. Landfills are scarce too. And what's the world doing about it? This is the most common mantra you hear when you think about how to, we need to reduce our consumption, we need to reuse whatever we can, and we need to recycle. Probably this is applicable to memory too. We should reduce whatever memory we are using in our workloads and applications, we should reuse how much ever the same data, maybe use it now rather than use more memory for it. And the locations and the physical memory recycle, we have been doing these things. But we probably may need to pay a little bit more attention. On one hand, we can try to fabricate more memories, but AI has made the need so much that may not quite, it may be hard to catch up. And there is so much importance for reusing, and recycling. So go to the first one of those, reduce. What are we doing in AI nowadays to reduce the memory we use? We talk about quantization. Instead of the 32-bit data, maybe we use 16 or 8 or 4, or even maybe binary neural networks with 1. So you can reduce. We have some effort. It's not every application, but there is an effort in that. We do pruning. And that reduces what we are doing maybe, but some reduction. Mixture of expert models. So we do not use all the coefficients at the same time. We only use what we need, or bring just the expert, some experts. That's reduction. So there are some things happening in AI to reduce how much memory we would be using. But look at the growth of our models. While it's true we give some effort or put some effort into reducing how much memory we are using, the models are just growing as we speak. Every day, every week, new models and lots of growth. It's not just that the amount of memory needed is growing, is becoming 4 times or 5 times the previous model. The bigger fact is, what is the relationship of the memory that's needed to how much memory you can have in the system? That, the orange line, is basically, this is a little bit dated, but 23, and the trends are the same. Trends haven't changed. So the orange curve is what GPUs have. And that's only growing so much. The green is how the models are growing. And that's the gap between the two. Up to 22, we could still afford to fit a lot of models. But since 22, the gap between how much the models need and how much memory exists in a GPU, that has widened. And you cannot fit models in GPUs. So that makes it worse. If it was, okay, it became 5 times, 10 times, 100 times, but I can still fit, that was a different story. I cannot fit. That makes this issue extremely challenging, and it's very important. We need to deal with this. But thinking, looking at this, AI reduce, probably that's not happening, because coexisting models, even if you do some quantization, some pruning, but the number of models you are using, the number of models that need to be coexist, everything is in models themselves increasing. So AI, most likely, the reduce is not going to happen looking globally at AI. It's not going to reduce the amount of memory that you need, because we love capability that AI has brought to us. The world loves that capability, and capability that wins over efficiency. So hardware, maybe we can talk about, I want to be efficient, I want to use the least amount of memory, but are my models capable, and is it the highest capability? So we probably will not reduce the amount of memory that we need, that we will use in AI significantly, no matter what all we are doing. But we should, there is no reason not to do it. And it'll just, if we keep saying, we should reduce the models, quantize them more, we'll just sound like the grandpa or the monk who says, last person to leave the room, please switch off the lights. It's just going to be boring advice. and the world is going to use more memory. Now let's come to the second one, reuse. So what is reuse traditionally in computer systems? Locality of reuse, caches have used that. In order to increase the amount of reuse, the same data used again, we do tiling and blocking, and we algorithmically increase the reuse historically. We have done many things in many computer workloads. But locality and parallelism often conflict. So the last decade, and with AI workloads, last decade or two, we have been moving in the direction of more parallelism. And when you have a lot of threads running, they all need some tensor. If we keep one copy of the tensor and every thread has to access that, things are not going to go to parallel. So we copy a lot of data. We duplicate a lot of data. And so with the emphasis on parallelism, which is necessary to do the computation in parallel, the reuse of even things coefficients that are needed multiple times, but we are probably keeping them in separate locations for each thread or each, So reusing more is not likely to happen. Parallelism wins over locality. Locality has been one of the favorite principles of computer architects. Professor Harvey Cragen, who was my colleague, he used to say there are only two principles in computer architecture. One is locality, and the other is pipelining. Everything else can be created by some combination of this. That's it. But this parallelism right now is going to win over locality, and most likely reusing more. Many algorithms are going to distribute data, and they are going to duplicate data so that you can compute more and you can use the computation resources more. So now we come to the third one, recycle. I am meaning by recycle in this context, we have some locations. We want to use that same memory location for another piece of data, and so the location is the use of it is being recycled, that context. And traditionally, caches, virtual memory, the replacement policies would handle this, and historically these things that used to work well. And we collect garbage in the best way so that same locations could be used again, free locations. But with GPU and CPU and the movement of data in between, there is a lot of shuttling of data happening, because models are large, things are not fitting. CPUs have more DRAM. GPUs have less high bandwidth memory. So when things are not fitting, there is movement of data between them, and the scale of shuttling is only increasing. So it is true, we are trying to use that location because there is no other location to use, but it leads to a lot of shuttling, and if you don't do it efficiently, you wouldn't benefit in performance because you are communicating way too much. Even in a simple GPU cluster, this is just 2 nodes, and the CPU, 4 GPU, each node has the 2 CPUs and the 4 GPU. There is NVLink, higher bandwidth. There is PCIe interconnect. There is NVMe and flash memory. So there is SRAM, there is DRAM, there is high bandwidth HBM, there is flash. This exists even in small memories. And each of those channels have different bandwidth properties. Each of the different types of memories have different capacities and different speeds. So previously, when we were managing the memory hierarchy, we were looking at, a little bit of cache, maybe L2 and L3, complicated things a little bit, but still the channels were more predictable. We knew what is coming from what can come from DRAM to the last level cache, what is the speed, what is the bandwidth. Now it's a variety of channels. And the variety of channels include, give you more possibilities, but it also makes life difficult, because if you do, if you make a mistake in your judgment as to where to put this data and which path to use to move it, you could be doing really poorly. So, and how to do that, it is complicated. So this favorite picture of us, our community, with the locality and large amounts of slow memory at the bottom and small amounts of fast memory at the top, and all the cache, the cache policies and the virtual memory policies would bring the right data to the top, and you have it at the top. It worked when programs had a lot of locality. Now that with the amount of parallelism we are exploiting, the locality that in effect you can get has reduced, and this basically, it doesn't seem to work anymore. And the complications in moving data across the hierarchy has increased and is increasing more, because we want to use large amounts of NVM, non-volatile memory, because the volatile, if it is non-volatile, you don't lose the data, you don't bring it when you start the system. Non-volatile memory. So there are different kinds of memory that is becoming feasible to use, and they all have different properties in terms of their capacity, their speeds, the bandwidth they offer. Now we have to kind of do linear programming between all these options in the fine phases of the program that we are executing in order to do well. It's not simple, it is becoming complicated. And the future is going to be even more complicated, because what's coming is the chiplet era. And chiplets, so you will have already in GPUs, we have the GPU chiplets and the memory chiplets and multiple memory blocks. And so they cannot be treated the same, because they are located different amounts of distance from the core that's computing. So even if the memories in this picture, actually I have the memories shown with different colors, but for a moment, let's simplify the left side picture. So the green things in the middle are the processing computing cores, and the sides, let's assume they are all the same in terms of capacity and bandwidth. But your distance from the core that needs the data, how do you place the data? How do you partition the data among the different memory pieces? And how far are you from whichever core needs that data? It's not a very easy problem to solve. And now on top of it, you assume that they are not all uniform, the same type of memory. Some are HBM, some are DRAM, some are PCM, or different types of memory. So the memory technologies are coming up with many more memories, and many memories which previously used to be simply experimental are reaching the stage of you can use them in a system. So when you can use these heterogeneous types of memories, even if you were only doing 2.5D integration, the 2.5D just means that the left side, which means there are the different chiplets sitting side by side, and there are connections between them can be routed in a little layer underneath them. And so the interposer layer helps to connect these pieces. But now there is even more variability in the speed of memory because of the distance. And then come to the right side where 3D integration is possible. Chiplets can be on top of each other. What are you going to put on top of the GPU? You put some HBM, you put DRAM, do you put flash? How many things? Are you going to put it uniformly on every GPU, or some GPUs will have more flash, or nobody knows. But this is the time Even architects have this opportunity to come up with systems, but unless software uses the system correctly, it's not going to work. And managing the memory, even in that heterogeneous environment, is going to be extremely important if we are to deliver efficiency for future workloads. Lots of 3D integration possibilities. Packaging of semiconductor chips was not something I was interested in for 25 or more years of my career. But the last 2 years, I am paying attention to it, because for the first time, packaging opportunities are giving me the chance to architect different types of systems and memory, and how much I can communicate the bandwidth offered by the memory, what types of memory do I want to integrate, and what does it offer me in terms of a better memory system. So there are more opportunities coming, but so with these 3D memories, basically you have this layer in between where you could be communicating a lot more. Much higher bandwidth is possible because the chips are close to each other. Also, if you look on the top right picture, packaging experts, and I'm not an expert, I just listen to them to understand what are my opportunities. Chips can be put, they call it back end of the line or front end of the line. You can put chips the same way, stack them up, or the opposite way, so you could, thermal management, different problems, but lots of opportunities to put chips in different ways compared to what we were able to do in the past. But all of those opportunities may help us to have more memory in the system, but it will also complicate the memory management. So why is this? Probably you know it. I shouldn't be talking to this community on why memory allocation and management are so complex. Coming from the application or framework, and with all the AI, CUDA, runtimes, kernel drivers, unified virtual memory management, the UVM, and then the hardware, the different types of memory, and then the CPU and the GPU shuttling the data between them. So many pieces in this picture, making it complicated. And allocating a large chunk of memory and managing fragmentation, balancing allocation speed and fragmentation, everything is complicated. And it was complicated enough on CPUs, and we try to optimize a lot. And optimization is the root of many evils. We are spending time figuring out what's the best thing to do, best way to do. So it keeps complicating the metadata, complicating the management of the metadata. So there is a lot going on there. And with multi-threaded applications, of course, the complexity increases. And either the metadata can grow, or the synchronization problems happen, and some cross-core metadata exchange. You have been working on techniques to reduce the problems with the multi-threaded allocators, but it's complicated, and this community has contributed a lot to that area. And lots of papers, the very famous Horde paper, and Catherine McKinley is my colleague for a bunch of years and friend, and we had Emery's paper this morning too. So a lot of things going on. Lot of allocators, and industry and academic works on them. If you look, activity, daily updates on how to allocate things better. And processor performance is highly sensitive to memory allocation, even with this. And this is CPU with 3 different allocators, JE-malloc, TC-malloc, and me-malloc. BFS, performance, this is the variability. And then another benchmark, Larson, And it's not the same in different programs, the variability. So different allocators optimize performance in different ways. There is no, it works for everything, one for all solution. And the complex metadata in the multi-threaded allocators lead to cache pollution and synchronization overheads. So we did some work on that. And if you increase the number of threads, the cache misses from the metadata side. So this is the darker section at the bottom of each bar is the cache misses coming from the metadata, and the other one is coming from the true data. So the metadata cache misses keep increasing when you have more threads. Similarly, the synchronization cycles as a part of overall cycles keep increasing when you have more threads. Naturally, we can understand because we are doing the metadata management, there is stuff to synchronize between the threads and it happens. So the metadata in these multi-threaded allocators leads to these sorts of problems. Now on top of all of those, the CPU to GPU communication is going to bring in another angle, another dimension to the complexity here. And the CPU-GPU data transfer and the management. When NVIDIA and the GPUs came by, first we allocate everything on the CPU side, CUDA malloc, and then you do a copy of the data to the GPU. That was how we started. There has been a lot of improvement, progress, more work, lots of work on how to make this problem better, or this problem solved. So the user space, there is the memory allocation in the CPU side. To the GPU, how you move it and how you control that transfer, there are a few different ways to do it. You can pin certain things to the physical memory in the GPU. You could do asynchronous copy. When you are computing, you could still be moving stuff ahead of compute and so on. The dream is to have a virtual memory, one address space. Whatever we were enjoying on the CPU side, can we have it with CPU and GPU together? That's the dream. That's the programmer's dream. I don't have to deal with this. I just think of it as one. But the GPU has the high bandwidth memory, but less capacity. CPU has the DRAM and lot more capacity. So we still have to deal with these transfer issues. And so CPUs were complex enough, but now with the CPU-GPU transfer, this issue has become even more complicated. So, and the CPU-GPU data transfer, the UVM, you could do on-demand data transfer at page granularity. Just, you don't do anything special. We just want to treat, the unified virtual memory. Or you have the pinned memory, and you can, the U1 line shows, whatever kernel you are running, you are moving the data for that into the physical memory. Or you can have asynchronous memory copy. The red lines are actually the same as the U2. The red lines are zoomed out representation of moving things from the GPU DRAM to the SMs or the compute threads of the GPU. So the shared memory inside each thread is going to get data through that asynchronous mem copy. And you would, without the pin memory or UVM, you would write code in whatever way. So you have more code to write. With UVM, it is simple. So UVM would be nice if it worked, if it gave the same performance as the other cases. But when you look, UVM doesn't give the performance. So at this point, UVM is more for convenience. It's not for performance. UVM is for convenience. The programmer productivity can be higher because it's convenient, but you do not get the same performance as async mem transfer or the pin memory. You could do better with those techniques, but it's more inconvenient and you need to think what you want to do and so on. So more than 4x performance deterioration when you go to the UVM, which is convenient. And these were some small benchmarks. We worked on this some time back, but recently we did some LLMs. And of course, what did virtual memory offer you one time? We could fit in applications that wouldn't fit in our memory. They would come as you need, and you didn't have to know anything about it. So if you take LLMs and you oversubscribe them, so the system doesn't have enough memory to fit everything, and the green bar, there is no oversubscription. The model can fit. The orange bar, there is like 2x, 2.5, 4x oversubscription. And the red bar, almost 5x oversubscription. So the UVM is going to manage the movement of data, and that's nice, that's convenient, but you lose a lot of performance. It's not even the 4x on the previous page. The 4x on the previous page was for tiny micro benchmark. For these, it is 1000x, something like that, huge. So it's convenient, but practically we cannot use it. Because if things are going to be this bad, that's not good. So we need to figure out a way to manage this data movement in a way that it still is feasible to use it performance-wise as well. So this is not, if you work on it, you can make it better. And so I have a student who is doing some work on it, and this is not published data yet, but preliminary data, we can reduce it by half or something. But that's not, what you are looking at here is not something, it's huge. So, but you can reduce it by about half by prefetching some models early in parallel. You have to carefully juggle this. That's what you have to do. And a lot of the data movement or memory management challenges are introduced by the KV cache in LLMs. In KV cache, there are the query token and then the key token. Q has to be multiplied by the key, and then the QK is multiplied with the value token to get the attention, and you continue this process. So the KV cache keeps growing, the QK keeps growing, and when you have to, as the batch size or the sequence length increases, the cache size that you need becomes large. You do not have space to keep it in your in the GPU's high bandwidth memory. What can you do at that time? You offload some of it to the CPU's DRAM. But then you have to bring it back because you need it. So you have to keep shuttling. But offloading KV cache is a technique that researchers have come up with in the last 3 or 4 years. A lot of work has happened in things related to this. So Paged Attention was a paper where the KV cache offloading, and then there is VLLM, there is Pi, there is a lot of work about how to do this KV cache offloading. So let us say this was, let's say we have a system with about 40 GB HBM in the GPU. So the KV cache keeps growing in different runs depending on the batch size and depending on things. It may be sequence length, it will grow. Can I let the KV cache take as much space, or when do I decide? So you put a cap on, okay, let's say I will give 26 GB for the parameters, 12 for the KV cache, there is intermediate data and other things going on, and 5% for the other stuff. Just think. If you, with a higher request rate or a larger batch size, KV cache may run out. And when KV cache run out, you can see when the request rate increases, percent of available KV cache is reducing, there is no more space to put anything, and the token latency is going to increase. And so the latency is 2.5 times higher when I increase the request rate just 3 times. So we do need to manage this well in order to get a reasonable token latency, reasonable performance, and space is limited. That's all we have to use. So VLLM, if you don't cache it, you have to recompute it. So do you want to recompute the KV, or do you want to cache it and bring it back? So it becomes this trade-off in save it, bring it back, or recompute. So when to trigger each of those operations, there are some heuristics different systems use to decide when will I push it out, when will I decide forget it, I'll recompute. And so we have some work. This is in SOCC last year, and this is, so the major works that had come up at this time to deal with this problem, they were all offloading KV cache. Offload KV cache, bring it back when you need it. So CPU DRAM has the parameters. You bring the parameters to the GPU HBM in the beginning, then computation starts, KV cache is created, KV cache doesn't fit, you swap KV cache into the CPU DRAM, and CPU DRAM has more space. You can grow the KV cache, partly in here, but the rest in there, but you have to bring it back as you need it. And you could transfer a layer in parallel to the compute to get better performance. You could reduce the latency up to 2x by doing things like that. That is what some of the papers show. And an alternative is, let's just remap the parameter, because even all the parameters are not used all the time. Different layers, you are computing certain layers. So you don't need to bring all the parameters to the GPU. Instead, you could be shuttling the parameters as opposed to the KV cache. You may ask, how does it matter? It matters because KV cache is dynamic and it changes, and you have to put it and bring it back. Parameters are resident in the CPU DRAM. It's not changing. So you just have to invalidate them here, and you just have to bring it one way, not two ways. KV cache, bidirectional traffic. Parameters, only one direction. Whenever you need it again, you just bring it back again. So that is what we did in this. Parameter remapping is unidirectional, and it's not dynamic data. That is what the model has. So there isn't as much overhead in synchronizing or bringing it both ways as in the KV cache case. And now several models coexist. Agentic AI, multiple agents working, when to trigger the remapping, which models to remap, how many layers to remap, which layers, so there are more decisions. Management becomes even more complicated, okay? So dynamically remapping the parameters, not the KV cache, to elastically resize the KV cache. That is what is done in this on a SOCC paper last year. And essentially, there is the metadata, there is the remapping controller, and the transfer engine. And we select, the scheduler will select which models to serve, because multiple models coexist. And inferences, you want to give the quality of service. You also want to get the lowest energy, best performance, lots of things, right? So scheduler does its job. Memory allocator updates the usage parameter and KV cache. And remapping controller determines whether to remap the parameters. Async transfer engine does the GPU-CPU transfer, and the GPU executes the LLM task. So this is what was done in this. And essentially what we did is, if you have so many layers, the kind of halfway away from you, that's the parameter we will send to the CPU. And when you send it to the CPU, hopefully we have enough time before we need that, we could bring it at certain time ahead of when you need it. So, so the running layers and the remap layers, the remapping controller manages it, and the details are in the paper. Probably in the interest of time, I'll just go through. So you don't want to be remapping the layer closest, or if you just use that and you know there is a lot of time to get there again, we could offload that. Offload doesn't mean you're moving it, you just invalidate it here, so we will bring it back later. That's all it will do. And Oneros, for time between tokens, time to first token, and throughput, it could beat VLLM and Pi, which are the prominent other methods to have, which did KV cache offloading. And details are in the paper. And we also saw that it is better to cap the number of layers you would remap. You don't just let you remap or send the layers out. When you, with a larger request rate, if you don't cap it, things may be bad. So you also have to cap how much you may ever remap. So lots of variables to engineer, and but if you can do a good job, you can get good performance, higher request rates, and better throughput, and so on. Microsoft's deep speed with this and Flash NVM and the NVM Express protocol, and this one was for training. This work was like 2 years ago, and lots of opportunities there as to what to offload and what to put where. The model state can be partitioned, and you can offload different things into the NVM. And deep speed allows many options. They call it 0, 1, 0, 2, 0, 3, 0, infinity. There are a few different choices. And you could offload different things. And on that system I showed, the small GPU cluster with the 2 nodes, we no, actually this was not on this system, it is on a bigger system. And, oh, I'm sorry, it is on this system with the 2 nodes versus the 1 node. And you could actually see, we could fit in bigger models on 1 node as opposed to more nodes. So in here, it is just on the single node. If you didn't do deep speed, the size you can fit is a lot smaller. With deep speed, you can fit larger models on 1 node and on 2 nodes. You could do that. But the more interesting thing is perhaps this one, the top picture, the achieved model size on a single node. The last blue bar shows what is the size of the model on the single node, and it is bigger than the one on the dual node if you offload into the NVM. When you have 2 nodes and you offload into the, so the 1 node, it's easier to offload to the NVM and get the benefit. You can fit the larger model. The second and the third set of bars show that your throughput is less, memory usage is more. So there are all the downsides, but simply the model fits, which is valuable for a lot of customers who do not have 2 nodes. They only have 1. And they would rather fit their model on that 1 node machine rather than have more GPUs. So there are different ways to optimize. Sometimes it is, yeah, it's possible, that's it. It's slow, it takes more memory, but it's possible. And other times it is, we just want better latency and better throughput. So you optimize and manage the movement in different ways. So with deep speed, the single node could achieve a higher model size than the dual node. And more details on that in this ISPAS paper from 2024. Recent, a lot of discussion on workload-specific management. It makes me a little bit sad. We used to be able to manage workloads automatically. Now all of a sudden we are like, we can't do that, it's not working, we need to manage more workload-specific. Maybe we will still, so this isn't working, but hopefully we can make it to work soon. We will figure out heuristics and processes to make it to work. And even when the 3D chips will come, we will still do it. But basically, temporally or spatially, we need to pay a price when we have the large models. There is no way to escape. Somewhere you have to pay the price. With the types of memories and the different bandwidth and latency considerations for each piece, CXL, which has been a big thing in the architecture world in terms of expanding memories, architectural innovations like PIMs. I guess last year there was the keynote on the PIMs. But PIMs, again, a big locality problem. This paper, this is Proteus, one of the PIM papers. If you look, it works for many workloads. Wherever matrix multiplication is there, it doesn't work. The things I have highlighted are when there is matrix multiplication, the first bar is GPU, and then there are PIMs, and PIMs, the performance is poorer compared to GPU because the locality, the matrix multiplication, the reuse is very high, and in PIMs you have to copy all the data or you have to keep shuttling data to where the compute is going to happen. So it's challenging. It's not very easy, and algorithmic innovations are needed to handle this problem. Different types of neural networks. In another part of my life, I do weightless neural networks, no coefficients. It's lookup tables, RAM neurons. It has fascinated me very much that I'm working on those. And co-designs. People like this conference, I guess between the morning and the afternoon, we are trying to actually learn from each other, and we need to do more of that. Because no one branch of science can solve this problem. This is, we need to work together on it. Different kinds of computing. So, and again, when it comes to FPGAs and hardware accelerators, another set of optimizations. We need to work on all of them. So, I would like to end with a note saying, there is memory management, there is something in it for everybody. Whether you like hardware or software, there is something in it for you. You are somewhere there, okay? And all these layers are important in getting this done. Whether you like algorithms or architecture, you have something in it to do. Plenty of opportunities for all to improve how things are happening. But, reduce, reuse, recycle, we need to think about this, work on it, but recycling the locations or the memory management, a big part of it, and I will end there. So thank you for listening, and I can take some questions.
So great talk. I think you actually set excellent stage for the following sessions. So all two papers coming related to what you said. Before moving on, if there's any question, yep, please, hands up. Anyone have any question? If no, then let me ask one question first. So in the middle, you mentioned about the unified virtual memory, but for example, Grace Hopper or kind of follow-up, which on Rubin, those systems have some unified CPU and GPU memory shared. Do you think that is really needed, or the kind of conventional separate memory space between host memory and device memory suffices for AI or LLM inference?
I think it's a good idea to have them. It's not working now. It's working poorly. But human productivity is a big part of all this. Humans are the most valuable commodity right now. Okay? So humans are a big resource, and creating applications will get speeded up. Bugs will be fewer maybe. And so it is a nice thing, but it's not working now in terms of performance. And so it looks like a bad idea at this point. But only if a lot of people work on it, we can turn the bad idea into a good idea. But I would say, in spite of the poor performance, we should do it. That's my personal opinion. Just in the long run, at some point we will reap the benefits, if not now.
Hi, very interesting. Nadav Amit, Technion. I wonder, in memory pooling area, which is different, many times people talk about overcommit ratios of not as high as you show here. And even in those cases where memory footprint is more known and we can do all kind of optimization, it fails many times. Like memory overcommitment ratio of 2 is not something that works well with memory pooling. So why would it be any different in this domain if we fail with much simpler access patterns?
I am not completely sure I understand the complications in the pooling versus this, but I would say, I think the biggest challenge as I see it is the capacity requirement for multi-tenant models is so high. It's not 2x, it's not 4x, it's way beyond that, that we have to work. It's not 1.1x, and it is not, it's not that small. And the way AI is used by the world, I don't think there is a way it will come down. It will only go up. So I think there is a difference in how much oversubscription is needed just because of that.
The fact you need something doesn't mean you can do it. So that's the only thing I'm trying to emphasize.
The only, so it's complicated, and the need is very high, the way the world wants things to work. Otherwise, we just have to say it is, it will be slower, it will be like that. But if, we should, I think, we have to figure out a way to automatically move the right data to the right compute at the right time, right? So, and allowing oversubscription as large as 10 or even 100, why would it not be possible? Because if locality was there, it would have been possible. For reasons I mentioned, it's not looking possible at this time, but maybe there are ways. If we keep working, we'll come upon something. That's my feel. I'm optimistic always.
Okay, I just have experience with NUMA. Thank you.
Yeah.
Great. Any other question? So then let's thank the speaker. Oh, sorry.
Steve.
Yeah, one thing I picked up from your talk was, or tell me if I'm wrong, but growing heterogeneity in the what's available compared to say 20 years ago, and what that means for people developing software. Here I'm trying to draw a bridge between the two, the morning and the afternoon. And I just wanted to know what your thoughts might be about that. First of all, did I read it properly that you foresee growing heterogeneity in what's available? And then the next part of my question is, do you have thoughts about what this means for the software community, in the sense that presumably if that's true, then it means optimizing for a much more diverse set of platforms, if that makes sense?
Yeah, I think heterogeneity will grow because capacity, price, considerations for some new emerging memories are very attractive to be used in systems. And so far we were living with volatile memories, DRAM and anything above that. And non-volatile memories are useful. We could design systems in different ways when we have non-volatile memories. So it will only become better. My colleagues in the semiconductor area, they are talking about lots of fancy memories, which they are saying is close to being actually fabricated and really made production. They have experimental small pieces, but they think it's coming. So in 10 years, 15 years, that sort of range, I believe it will be heterogeneous. Now, what should software developers, should you go learn all these different types of memories and then try how to program? That's why I argued for the UVM. Okay? It doesn't make sense for software developers to have to understand all the intricacies of all these heterogeneous memory. That is why we should develop something that will work like the virtual memory that we used to have. So the UVM, in spite of bad performance now, I really think we should work on it just for that sort of reason. Yeah, we should free programmers from this. And so we should come up with ways to free them so their productivity is high and bugs are fewer. Yeah.
Okay. With that, let's thank the speaker again.
Thank you.